Okay, good evening, everybody, and welcome to this virtual meeting of the Royal Meteorological Society and the Science Behind the Greenhouse Effect by Professor Joanna Haigh. Before we get the meeting started, just a few housekeeping things at the beginning. Just to say that don't forget you can join the WeatherClub. Full access you can find on the WeatherClub site. There's information about events and meetings there, opportunity to participate in activities such as the Great British Weather Experiment. There are competitions. If you have questions of experts, you can ask them there at the Weather Club, and you'll get a quarterly newsletter full of weather news and stories and features. So if you're interested in the weather, don't forget to join up to the Weather Club. And of course, if you're not yet a member of the Royal Meteorological Society, then of course you should be. Anyone interested in meteorology or climate change can join. Of course, what I would say is the best and the greatest leading society for meteorology and climate change. Our worldwide membership is made up of professionals, enthusiasts, academics, students, teachers, and anybody really who's interested in the weather and climate. The benefits of your membership would include the monthly weather magazine, discounts at conferences and our paid meetings, all our paid meetings. We have a full program going ahead over the next 12 months, of course, virtually because of COVID, but there will be as active as ever in terms of our program of meetings. You get discounts on our journals, including a brand new journal, Climate Resilience and Sustainability, access to support and grants, and of course, discounts at the Royal Meteorological Society shop. So after the talk, which will last about 30 minutes, we'll have a Q&A session. So hopefully we'll have about 30 minutes at the end for questions as well. Please use the chat area. I can see many of you are already using the chat area on the right-hand side. So thank you for that. And hello from everywhere, from Sheffield and Mexico to Brazil. Yeah, please use the chat area on the right-hand side to ask your questions. Once the presentation starts, do restrict it to just questions on the presentation and try and keep your questions short and of course relevant to the presentation. If you write a very long question, then that's the only question I'll be able to see, unfortunately. And please be aware that I may not have time to call on all of the questions that are being asked. So we'll move right on to the presentation. Oh, just one more thing, about 3 talks that are coming up. All, of course, virtual webinars or virtual meetings. So we have a virtual webinar on Tuesday, the 24th of November, which is around our meteorological applications journal, where you can meet some of the authors of that journal, Robert Neal, who's a scientist from the Met Office, and Dr. Vicky Volt from the Department of Meteorology at the University of Reading. And then the very next day, on Wednesday, the 25th of November, there's a virtual meeting around forecasting for dinghy regattas and how to give sailors a useful forecast. And that speaker will be Simon Rowell, who's a meteorologist with the British Sailing Team. And then on the 2nd of December, there's a virtual meeting on Nature's Calendar, recording the phonology in the UK, and with a speaker, Professor Tim Sparks. So as you can see, we have a full program of meetings coming up, and you don't even have to leave the comfort of your own home to attend them. So I'll move on to tonight's presentation. We're delighted to have Professor Joanna Haigh talk to us today. Joanna is very distinguished. She is a CBE and Fellow of the Royal Society. She's an atmospheric physicist and was, for 5 years prior to her retirement, the co-director of the Grantham Institute on Climate Change and Environment at Imperial College London. And before that, she was the head of Imperial's physics department. She's published widely in the area of climate modelling and radiative forcing of climate change. And I think she's probably best known for her work on how changes in solar activity affect the climate. So I'm going to switch off my webcam now and ask Joe to switch hers on. And Joe, over to you, and off you go. Really looking forward to hearing what you have to say.
Thanks very much, Dave. Thank you to the RMetS for giving me this opportunity to do a talk. It's a talk about the science behind the greenhouse effect. And so I suppose I better, it's flicking to and fro. Just make sure everybody understands what the greenhouse effect is. I'm sure most of the audience of the Royal Meteorological Society are very well aware of this, but the point is that all the energy driving the climate system comes from the sun, and about 50% of that reaches the Earth's surface, and the surface gets warm, and that emits heat or infrared radiation. But while the atmosphere is, 50% transparent to solar radiation, it absorbs 90% or more of the heat radiation that's emitted from the surface. The atmosphere gets warm and it emits heat in all directions, including back down to the surface. So the surface ends up being about 30 degrees Celsius warmer than if there were no atmosphere here. That's fundamental understanding of the climate system. And the talk today is going to be about the history of understanding of the greenhouse effect. Now, I was asked to do this by the METSOC as what they call a taster talk, because there's a meeting in May on the history of climate science ideas, and I'm the person doing the greenhouse effect, which is great fun, and I'm enjoying looking all this stuff up. But I should point out, as you've heard from my CV, I'm not a professional historian, so I enjoy doing this thing, but I'm not good at historical analysis or anything like that. Anyway, so in the talk now, I'm just going to go through some of the historical ideas and how they were developed, something about some of the scientists that were involved, and actually there's quite a lot of them, so I can't possibly cover everybody, and also try and put that in the context of what we actually understand about the science behind the greenhouse effect today. And actually, I'm just going to stick to a couple of the major misunderstandings or factors that people seem to get confused by. So the first person I'd like to introduce here is Edmé Mariotte, who's French, and you can see his dates there, lived in the 17th century. And in his monograph on the nature of colours in 1681, he noted that light and heat from the sun easily pass through a sheet of glass, but that heat, and he was looking at candles and other sorts of sources, doesn't. And so this is a sort of background idea towards what we now call is the greenhouse effect. He didn't coin that term, but you can see that this is getting towards similar sort of ideas. And the next person on the list is Joseph Fourier. Now, he is widely identified as the father of the understanding of the greenhouse effect. He was, of course, better known for initiating, he was a mathematician, initiating Fourier series, which developed into Fourier analysis, and he was applying this to problems of heat transfer and vibrations. He was very active in the French Academy of Sciences, and he had a number of interests, mainly from a mathematical perspective, but he did wonder what determines the surface temperature of the Earth. And he did a calculation of the energy balance, given the energy coming in from the sun and the energy going out in infrared from the Earth. And he worked out that the temperature should be much colder than is observed. In fact, it should be well below freezing. So that set him off thinking about trying to explain what was going on. Now, he thought perhaps the atmosphere acts as a sort of insulator. And so this is a sort of beginning, again, to understand some of the physical processes that we now call the greenhouse effect. But he didn't know that the atmosphere trapped infrared radiation. And he actually concluded that gases in the atmosphere formed a sort of barrier like a pane of glass. Now, at the same sort of time, he was trying to do some mathematical calculations of these things. And the calculations that he did actually included conduction and possibly convection, but they didn't include infrared radiation. The only radiation that are in his calculations is solar radiation coming in. So he is getting at the ideas, but he's not actually proposing the right solution at the moment. And that actually came down to another Frenchman, Fourier, who was a great physicist. One thing he was famous for is the Fourier effect, in which it's when you have an exothermic reaction that takes place when a liquid is added to a powder. He developed a power heliometer, and that was the first quantitative measurement of solar constant. He did work on all sorts of things, solar heat, optics, photography, as well as meteorology. But in the context of this talk, what he did understand was that the gases in the atmosphere, and particularly he speculated water vapor and carbon dioxide, might trap infrared radiation, thus warming the Earth. And so I think actually, although he's not usually acknowledged to be the sort of first person to understand the physics of the greenhouse effect, I think he should be given that accolade. He did a calculation in which he had the infrared radiation coming up and it being re-emitted in all directions. His calculation was actually wrong because he had an incorrect radiation law, but the concept is absolutely right. So the next person that I want to include is, oh no, I've got the wrong, doesn't seem to be working. Yeah. I'll do this. Oh, there we go. Is Eunice Foote. Now she's an American lady amateur scientist, and she was doing laboratory measurements, understanding the absorption of infrared radiation by different gases. She was actually looking at wavelengths of radiation that are really more appropriate to the sun, so light and near infrared, not thermal infrared. So she wasn't actually simulating what's going on in the atmosphere so well, but she does say, I can't use a pointer on this thing, but somewhere in that text down there, it says an atmosphere of one of these gases would give our Earth a high temperature, and if at one point in history the air had mixed with a larger proportion than at present, an increase in temperature would result. So she is actually, I think, the first person to suggest that more CO2 in the atmosphere would give you a warmer climate. She wasn't, I think she could have presented this herself to the American Association, but the paper was actually presented by a man, of course, and she's received very little recognition for her work. Moving on, we have the person who is very well, my clicker seems to have stopped working, so I'll have to use something else, who is very well acknowledged for his work, which is John Tyndall, and he was living in the late 19th century, and this is his apparatus to measure absorption by infrared gases. And you can see there's I can't use a pointer, so it's a bit difficult to explain. There's a long sort of metal tube there, and you'll see on the right-hand end there's going to be a hot box, and the radiation comes through the tube and into that conical assembly on the left, and also on the other side of the conical assembly is heat coming in from that Leslie's cube through a heat screen. So when everything is starting up, there's a thermopile in the middle of that conical assembly, and the wires go to the galvanometer that you can see on the middle table there. And so you can get a measure of the temperature that's given by the heat that's coming in from both sides, and you can balance the galvanometer to a 0 point at the start. Then the gases are introduced from the container that's on the floor on the bottom left through some wiggly tubes, you can see, up through a pipe, in through the taps at the top, into the black metal tube that's along the top there. So this is what Tyndall was doing. This is his apparatus, and he introduced different gases into the tube and looked at how much of the heat was absorbed from the heat source before it hits the thermopile. So we started off by looking at sort of various organic gases like ethane and ethylene and these sorts of things, and they had quite a big effect. But then he moved on to looking at gases that might be more relevant to climate, and he found that oxygen and nitrogen, and indeed air and hydrogen, had very, very little effect. Ozone he studied, which is quite interesting, and he found that there was some infrared absorption, as we well know. And then he moved on to looking at carbon monoxide, carbon dioxide, hydrogen sulfide, and nitrous oxide. And here he was measuring a signal, but it was a much smaller signal than from the ethylene and ethene and the organic gases. So with the organic gases, he found that there was, for a small amount of gas, a linear absorption between the amount of gas and a linear relationship between the amount of gas and the absorption. So this is what we would understand. But it went away from linear as you got to more and more absorption. But when he studied these atmospheric gases, carbon monoxide and carbon dioxide, etc., he says the action of these gases is so much feebler than that of any of the vapors referred to above, that he didn't try doing any more relationships like that linear one, because they were all low absorption. So then he thought that if you're looking at these absorption properties, and if these gases are in the atmosphere, they must produce a change of climate, and particularly the water vapor or carbon dioxide. He also mentioned that the hydrocarbons would also have a great effect on climate if they were in the atmosphere. But he also understood that it's not necessary to have to know much about the atmosphere in terms of its density or the height or where the radiation is coming from. Just a slight change in the composition would cause absorption of more heat. And so he says such changes, in fact, may have produced all the mutations of climate which the researches of geologists reveal. So that's quite an interesting statement. And I've got some numbers here, but I won't go through them now. It also, I thought I had on a previous slide. Should I try and get a previous slide? Yes. This was the Philosophical Transactions was the paper where he published all those results that I just mentioned. It's quite a long paper, and he goes through all these different gases that he studied. He describes his experimental setup in great detail, but it's a great paper to read, actually, if you can get hold of it. It's just explaining everything he tried and how it didn't work, and then he did something else, and then he got all these results. But then he thought further, and he understood that if he was going to do the job properly, he needed not only to consider how much of the infrared radiation the gases absorbed, but also how much they emitted. And that little drawing on the left is his sketch of his equipment that he used for looking at emissions of radiation by gases rather than absorption of radiation by gases. So what you've got there is a spherical, I think it's called an argand something burner, and it's got it gets hot, and so there's hot air arising above the sphere. The screen there is so that the thermopile doesn't detect the direct heat of the sphere, but just the heat indicated by those little arrows, which is coming from the gas, but in this case in the air. And then you start releasing the gases from holes around a cylindrical container around a sphere. So you've got the hot gases then, not just hot air. And again, you can do a balancing with the heating cube on the left before you start introducing the new gases. And you can work out how the gases that you're interested in are emitting. So this is essentially the basis of the information that would go into what we understand now about radiative transfer, and in particular Kirchhoff's law, which Kirchhoff published at about the same time as this paper was published. So this paper was 1861. I think Kirchhoff published his law in 1859. So the idea is that a gas that's good at emitting is also good at absorbing when everything's in thermal equilibrium. And that's fundamental to understanding the radiative transfer through the atmosphere. So we've already had geologists mentioned, but they play a key part in this story. And I'm going to move on now to my first geologist. This is Arvid Högberg, and he's interested in how CO2 on long-term changes and how that might affect the atmosphere on geological timescales. And he actually was the first person to do what you might call estimates of a carbon cycle, looking at sort of natural geochemical processes, including emissions from volcanoes and uptake by oceans. And he actually had this new idea, which was that CO2 from industrial sources might be adding to the CO2 in an atmosphere. And you can see I've tried to shade in yellow there. He's looking at the amount of CO2 that's emitted by industrial processes into the atmosphere, and he says it's quite small. It's only adding 1,000th part of the contemporary concentration. But even though that it's small, it's actually compensating for the natural amount that's on the timescales that is consumed over the same period. So he's pointing out that this carbon dioxide coming from industrial sources, it may be significant, especially if it continues and accumulates further. My next geologist is Thomas Chamberlain, and he's trying to understand glacial, so interglacial ice ages and why they come about. And so he, again, is one of these people who's a very, I don't know if you can call him Renaissance man, but he did lots of different sorts of science that he was studying, including how the sun produced its energy, and he suggested it's coming from some sort of atomic energy. So that's quite an interesting idea. He also published things on the philosophy of science and an inspiration for the approach that we now call, or philosophers now call, strong inference in interpreting results. He also, in terms of the climate change and geological timescales, believes that living material, so life, was greatest at periods of milder climates, and this is encouraging him to do this work. So I better get a move on. I'm going to run out of time if I'm not careful. So we come on now to the person that you've probably most associated with the greenhouse effect, and this is Svante Arrhenius, who's Swedish chemist, physicist, and he was the first really to predict that emissions from industrial processes were large enough to cause global warming. And his estimates here, which he published in that philosophical magazine back in 1896, he suggested that a 40% decrease in atmospheric CO2 could trigger an ice age, and similarly it would come back the other way. And he also calculated that a doubling of atmospheric CO2 would increase temperature by 5 or 6 degrees. So I was going to read a quote from him. Since now warm ages have alternated with glacial periods, even after man appeared on the Earth, we have to ask ourselves, is it probable that we shall in the coming geological ages be visited by a new ice period that will drive us from our temperate countries into the hotter climates of Africa? He also says, by the influence of increasing percentage of carbonic acid in the atmosphere, we may hope to enjoy ages more equable and better climates, especially as regards the colder periods of the Earth. So he's suggesting that we will be able to essentially prevent ice ages and also feed the growing population of the world. So the science here seems to be quite well established, even if the details aren't fully understood. But the next person we have on the list is, oh, I was going to, talk about ice ages. Yes. So just very quickly, this is graphs from the ice core in Antarctica of a carbon dioxide as a red curve and temperature as a blue curve. And you can see it's going up and down, and the lower regions is ice ages and the higher values are interglacial periods. And what we've got here, I think is currently understood, is that changes in the Earth's orbit around the Sun, particularly the eccentricity of the Earth's elliptical orbit, kicks the climate in one direction. So, for example, if it was trying to warm the climate, then what you'd get then is a little bit of warming, but then carbon dioxide and methane get released from natural stores in clathrates and ocean sediments and other places. And of course, because they're greenhouse gases, they cause the climate to warm. That means that there's more release of those gases and you get a very fast increase, which is that sharp bit of the sawtooth warming. And then when the eccentricity bit turns off, you slowly go back the other way. So that's, I think there's a lot of details that are not yet fully understood, but that's very much, justifying and supporting what Arrhenius's ideas were. But back to the science, I wanted to mention Knut Ångström, who's the son of the Ångström whose the unit is named after. And he claims that this physics didn't work because he understood about the absorption properties of the different gases, and that the CO2 absorption overlaps water vapor absorption. He also said that because CO2 absorption is so strong, there's enough in the atmosphere to saturate out, and no more radiation can get absorbed. So essentially, CO2 absorption is saturated, and adding any more won't make any difference. Now he was these ideas actually caught on, and the whole subject was put onto the back burner for quite a while. But what I wanted to do now was just present a little bit of science quickly about these effects. So this is a spectrum of in the thermal infrared of water vapor and carbon dioxide. This is just absorption coefficients per unit mass, so it's not atmospheric concentrations. But what the point of this slide is that you can see how very different the spectra are and where water vapor isn't absorbing, CO2 is. Then if we look at this spectrum of radiation leaving the top of the atmosphere, you can see that the red curve is the black body function of the emission from the Earth's surface, and the blue and black is what's actually leaving at the top of the atmosphere. And what we've got here is a very spiky picture, obviously, and there's different gases identified there. And in the next slide, I can show that effect in more detail. The left-hand side, the black curve there is similar to the wiggly curve on the previous slide. So that's the spectrum of radiation leaving the top of the atmosphere. And there's other calculations in there with the water vapor removed. And then you get the red spectrum, and you can see it's mainly having an effect at the short wavelength ends and the long wavelength ends. And then if you remove the CO2, it's having an effect in that gap in the middle. So it's quite extraordinary. I don't think it's a coincidence. I'm not sure if it's a coincidence, but it just so happens that CO2 absorbs very strongly where water vapor doesn't. So the picture on the right there is the difference between the colored curves and the black curve. And you can see the effect of the CO2 in blue there and the effect of water vapor in red, and the integrated effects in numbers, watts per square meter. So water vapor is definitely has the greatest effect, but CO2's well in there. And in terms of I was going to do, yeah, right. This is carbon dioxide concentrations in the atmosphere. This is a lovely plot from the old IPCC 2001 report, and I haven't got time to go into it in detail now. There's lots of different panels on different timescales going across millions of years, hundreds of thousands of years, 10,000 years, 1,000 years, and then very recently, and you can see this little 400 part per million mark on each of these plots. So carbon dioxide hasn't been as it is now for at least 3 million years and probably more. So it's very unusual. And this is talking about why CO2 is not saturated. And the point is that while it is saturated in the center of the absorption band, it's not saturated in the wings. I haven't really got time to go into that. So I wanted to mention this person, Nils Ekholm, who I think, but I haven't heard otherwise, I think he was actually the first person to coin the phrase the greenhouse effect. So while Fourier and others referred to slabs of glass, they didn't really describe the physics properly, and they never referred to like a greenhouse. So I think Nils Gustaf Ekholm can be given that honour. And I also wanted to include this lovely quote from him he gave the lecture at the Vostok at its jubilee in 900 as a humble expression of homage and gratitude by the author. So I thought I should say the same thing to the Vostok. Thanks very much. Right. And now I can't leave without mentioning Stewart Callendar, who of course was the first person who actually said that he noticed that the temperatures are rising and related that to rising CO2 concentrations. So in the bottom curve there, you've got his Earth's annual departures from the average from 1880 to 1930. He published this in 1938, again in the Vostok QJ. And then he collated a lot of temperatures from across the Earth, and integrated over the Earth is the one at the bottom. But you can see also on those plots, there's little dashed lines. Can you see dashed CO2 effect? And he's noticing that the CO2 could produce that upward trend. So I think that's a very good point. I was also going to show the current temperatures. If you look from 1880 to 1930, you can see it's bigger upwards towards the end, which is exactly what Callendar was showing. And then perhaps I'd better finish with the next slide, which is this table here, which he's got. You can see he's got different dates. 1900, 20th century, 21st century, 22nd century. I'm sure, sorry about the poor quality of the slide, but you can see the partial pressure of CO2 going up from each century to the next. But by the 22nd century, he still only got to 3.6 in units of 10,000ths of an atmosphere. So that's 360 of our parts per million. So that's way below what we have now. So he was very right on what's going to happen in terms of CO2 and climate, but very wrong in what CO2 was going to do. So I think I better stop there. Thank you.
Just a reminder to you all to please use the chat area on the right-hand side of your screen to ask questions. So please go ahead and start asking your questions now. Obviously, make sure they're relevant to the presentation, and I apologise if I don't have time to get to them all. So before the questions start coming in, Joe, perhaps I'll take Chairman's privilege to ask the first question. Given that most people think that climate change only, the science of climate change started in about 1990 with the climate conference and the IPCC. Given that it's actually got a history of several hundred years, why do you think there are so many sort of climate deniers who deny what is basically fundamental
I think
science?
I can't answer why they have this strange sort of mental aberration, but there's certainly people who don't want to believe it, and they'll grasp onto any reasons. I read one paper recently that was by a scientist that was actually a historian of science, and so I was reading about his views, and he said exactly what you just said, but round the other way, that nowadays climate physicists declare that Fourier said it was greenhouse effect was working because they want to be given respectability for their science by saying that Fourier had suggested it, which is a lovely turnaround. I do think, however, that the number of people who are denying the science is definitely going down, and if you look at the reaction to Boris Johnson's recent announcement, I know we don't want to get into discussing that so much, how good it was, but there was very little, I saw very little hostility. I mean, on various comment sites on the BBC, you get, you know, the usual suspects, but I think that mostly the general public understands now that we need to do something about climate change and just wants to know what they have to do to get there.
Mm-hmm. So we'll start turning to the questions in the chat. The first one's come in from Matt. What concentration of CO2 would be needed for a runaway greenhouse effect to begin?
So we're unlikely to get to a runaway greenhouse effect on Earth. You have to, with a runaway greenhouse effect, what happens is that you, as I described a bit with those ice ages, you get more water vapor, and then you get more carbon dioxide, and then it carries on going. But at Earth, the distance that we are from the sun, you don't get past the point where the water vapor gets saturated and rains out. So you don't get a runaway greenhouse effect on Earth, like you might do on other planets. So that's a bit of a vague answer, but I think that's correct.
Okay. Next question from D. I've heard one or two climate scientists use the phrase blanket gas rather than greenhouse gas. Is this a better term?
I think it is. You see, there's a lot of confusion about this because greenhouse is not a very good phrase to use. It's caught on, and I was sort of, praising Ekholm for sort of coining it, but it's not. The greenhouse effect doesn't work like a greenhouse. The greenhouse effect works, as we've discussed, due to the fact that it lets solar radiation in and it doesn't let infrared radiation out. A greenhouse actually just works by trapping convection. It doesn't let the air escape. And so some radiation gets in and it stays there because the air heats up and can't get away. So it's greenhouse effect is a bad phrase, but we're sort of stuck with it. So I think blanket is rather a good phrase because it's exactly what's happening is you've got a warm body under the blanket and the blanket's trapping the heat in. So perhaps we should have a blanket effect now. Yeah.
Okay. Next question. Have the feedbacks involving, and this is from Nigel, have the feedbacks involving clouds and the oceans been anywhere near sorted?
Right. Can I've got a few more slides, but I could include, can I show another slide? I assume yes.
If the technology will cope with it, yes, by all means.
Where are they? I'm not quite sure how I change them now.
I think if you just keep going. If they're at the end of your presentation,
okay.
Can you?
So there's some more slides
to go down?
here that it doesn't seem to want me to change. I don't know who changed. Oh yes, okay, right. I've got some more physics questions. Right, okay. I'm not doing this stuff. Oh yeah, radiative forcing climate sensitivity. So so this is a very, very hot topic, and climate sensitivity essentially tells you how much the globe will heat up, surface temperature will go up, given a certain change in CO2 concentration. Particularly, it's defined in terms of CO2 doubling. And if you double CO2 and you allow the atmosphere to equilibrate, which of course would take hundreds of years in reality, but this is a theoretical, hypothetical situation. You want to know what the temperature would be, and that's called the ECS. Now, if you do a simple black body calculation, as is shown there, using sigma t to the fourth for flux, and if you double the CO2, the change in flux is about 3.7 watts per square meter, and you use that, you'll get a change in temperature of 1 degree, but that's because it doesn't take account of the feedbacks. And the feedbacks, as the question, I'm sorry, I didn't notice the name, was commenting, is because there's all sorts of factors that make it different from the 1 degree. There's the fast feedbacks like water vapor, which is what Arrhenius and others were including, but also a much more complicated clouds and things like sea ice, which will affect the temperature. And then there's the very slow feedbacks which come in on those geological timescales, and they all depend on location, the background climate state. And I just want to show you this picture here, which is about evaluating ECS. So in 2013, the Intergovernmental Panel on Climate Change stated that ECS was most likely to lie in the range 1.5 to 4.5 degrees Celsius. And that range really hasn't changed much over several IPCC reports. You can calculate it based on historical measured data on CO2 and temperature, on paleo data, such as the stuff I showed you from the ice cores, and also using models. You can use energy balance models, or you can use climate models of varying sensitivities. And that bar chart on the right, which I don't expect you to be able to see in any detail at all, but what it's got, each horizontal bar, it comes from a paper by Knut et al. In 2017. Each horizontal bar is a group's different estimate of climate sensitivity and its range. And that blue vertical line is the 1 degree, which you get without the feedbacks. And you can see almost uniformly, people think that the feedbacks are going to end up being positive. So you can hypothesize negative feedbacks like, changing in albedo, but you can see all of these are tending to be positive. The grey area there is the IPCC 1.5 to 4.5 degrees. Now, this paper was published in 2017, so you might ask, has the science moved on? And it has. There's an awful lot more understanding being going on, but things just get more complicated. And people are trying to understand about how different sorts of clouds affect different patterns of clouds across the globe, affect ECS, and how these changing patterns of clouds. And my understanding of the situation is that there is a narrowing of the range, but not much of the expected value. So we're probably still at around 3 degrees, which is pretty much what Arrhenius was suggesting back then for equilibrium climate sensitivity. But with a big range of uncertainty.
Okay. So the next question is from Barry. Do we understand what effect the thawing of the permafrost will have?
So I think in principle, we understand that it's going to release particularly methane, which is a strong greenhouse gas and is going to enhance the greenhouse effect. And it's measured, it's observed to be melting at the moment, not at the rate at the moment to produce what has been called a tipping point, whereby the whole thing melts and then we're all in a new climate regime. So I think, again, this is very much a subject of current research. It's the effect of the thawing of the permafrost is definitely to enhance the warming, but the question is how much? So again, that's not an answer. It's posing the question in a different way.
Okay. Okay, so the next question is from Ken. What is the history of the measurement of CO2 in the atmosphere? And at what point did it become clear that CO2 is actually increasing in the atmosphere?
So that plot I gave with lots of little can I show that again? That was from the IPCC. Which over different time periods, and of course there are different techniques used in each of these panels, and as you go further back in time, of course, it's much less certain. So that first panel is actually done using ocean sediments. So they core deep ocean, in the deep ocean, cores of the sediment, and they can deduce the date of when the sediment was laid down and the carbon dioxide that's in that was laid down at the time. The ice core, the Vostok core there, the CO2 in that, I think, is done by analysing little gas bubbles that are trapped in the ice and deducing what the CO2 was then. There are other techniques like, I think for the very, very old dates, you can use certain sort of leaves. All talking right outside her range of expertise here, grow in different sorts of ways, and you can see in the fossilized leaves, the patterns of their growth tell you something about how much CO2 there was at the time. So that's a very, very old dates. Then as you come to more recently, you can look at other measures, and as you come into recent times, so that the plot on the right there is from the actual measurement at Hawaii. This is called a Keeling curve, because Keeling established in, I think it was back in 1950 something, a station on Hawaii. This is very clean airs, and so this is like proper measurements of what the CO2 is doing. And I hope that's not Ken Bignell asking the question, because if it is, I think he should be giving the answer.
I think the question was more how long, not the sort of techniques for measuring the past. I think the question was more about how long have we known that CO2 is, it was more of a history question. When did we first know that carbon dioxide was increasing in the atmosphere? The burning of fossil fuels.
Essentially, Guy Stewart Callendar, who put those things together. Well, that was the industrial CO2. So I suppose the geologists who were thinking about, the geologists that I mentioned in the middle there, back in the 18th and 19th century, must have got some idea that the CO2 was going up. But I'm afraid you can tell I don't know the answer to this question.
Okay. So the next question is from Andrew. How long do each of the greenhouse gases survive in the atmosphere?
That's a very important question. And CO2 has a very long lifetime. Its lifetime is probably, say, 200 years and more. So you can essentially consider it as almost forever. And this is the basis of the whole concept that you may have heard of a carbon budget. So we have a carbon budget, and we can only burn up the fossil fuels that give us the carbon that go into the budget before we reach a threshold temperature that we might not want to exceed. So it might be the Intergovernmental Panel on Climate Change says 2 degrees or preferably 1.5 degrees. So because CO2 is very long-lived, and because the temperature increase is essentially proportional to the accumulated CO2 in the atmosphere, it means that we just have to stop emitting CO2 sometime in order to not pass any threshold. I mean, it might be 1.5 degrees, it might be 5 degrees, but whatever it is, you just have to stop, because any more will make you go past it. That's CO2. Other greenhouse gases are shorter lived. So methane, I think, has a lifetime of something like 8 years. I hope I've got that right, but it's definitely shorter than CO2. And so it's actually also per molecule a much stronger greenhouse gas than CO2. So there are various measures of the sort of combined effects, and you can have something that's called a global warming potential that gives you the potential of that gas over a given time period to warm the atmosphere. Some gases have very short lifetimes in the atmosphere, and then you don't really need to worry that their greenhouse properties are very, very high. So you can see it's very, very different for different gases. And if you look in one of the IPCC reports, you'll see a chapter on radiative forcing with lots of different gases in, and how much they are and what sort of temperature effect we can expect from that.
Okay, the next question is from Philippe. Many people deny that the carbon dioxide effect mentioned in the past. Carbon dioxide was even higher than it is at the moment, and the temperature was not as high. So can you explain how this has happened?
So if you go back, we got the slide on here. If you go back in the very, very far distant past, the whole Earth, if you go back to those hundreds of millions of years, the whole Earth was still evolving. I mean, the continents weren't in the right place, and the volcanoes, it was still lots of gases coming out from the sort of primordial Earth. And so the atmosphere is just not the same. And it did go through very, very hot periods then. But once it's settled down into its current, you could say its current state, so maybe hundreds of thousands of years, the CO2 hasn't been higher than it is now, and the temperature has not been higher either. So I think that the answer is that way back then, hundreds of millions of years ago, everything was different. So that if you were going to try and understand what's going on then, you'd have to know all about the geology and everything else that's going on.
Okay. Nigel asks, when will the physics catch up with the huge increase in computer power to give us realistic projections in regional changes due to global warming? And particularly, he's got a particular interest in Southwest England, which I can
well,
second.
I mean, the Met Office is continually asking for new computers. They've got another great big one coming soon, I think, that they can use for both weather forecasting and climate. The European Centre for Medium Range Forecast has also got an absolutely massive computer, and I think it's the size of the computer which essentially limits the resolution with which they can do these forecasts. Having said that, the atmosphere is incredibly complex, and it's going down from scale to scale to scale. You look out the window and you see some clouds, and the beautiful fluffy little clouds. They are on many, many scales that no computer model is ever going to simulate properly. I mean, you can mesh your cloud models inside your big computer climate models, but there's all sorts of different scales there. So you're always going to have some sort of parameterization, or indeed some sort of stochastic arrangement for accounting for things that are happening at sub-grid scales. So I think the Met agencies think that the higher, the faster the computer, the higher resolution that they can have, the better. But there's bound to be a limit to that, and it may be that there's a sort of, perhaps at some point we can stop and think about other ways to represent the sub-grid scale.
Yeah, so maybe it has to wait a little bit longer. So a question from Danny, and it's more of a social question rather than a science question. Are you optimistic about our ability or desire to manage climate change?
Yes, I think so. I mean, it's incredibly hard. And it's going to take the whole globe, and it's going to be a huge effort, and all sorts of changes have got to be made in the way that we do things. But we're getting onto the right foot now. The government at least seems to understand there's an issue. Certainly, the United Nations understands that there's an issue, and we had the Paris United Nations meeting, which was hugely encouraging in the sense that it was a unanimous agreement of all the 150 odd countries that they were going to do something. Of course, the slightly more unnerving bit of it is nobody has done enough, and indeed they haven't even done what they said that they would do. But if you listen to Boris Johnson now, the promises that he was making last week are nowhere near enough, and not getting anywhere near the scale that's needed to get us onto a zero carbon future, or zero carbon by 2050. But all these things are getting set in motion. So people thinking about moving to more electrification of transport and of heating, and of ways of phasing out fossil fuels and using alternatives. And I think when humans decide they're going to do something, and they're very, very imaginative and innovative, they can do it. And it just means that what we've got to understand now is that actually the impacts of not doing it are going to be much worse than than paying for it and doing it. So I'm certainly optimistic about our ability, and I think about our desire to, at least some people.
Okay. Question from William. How many ensemble members are there in a climate simulation? I understand that the Met Office has about 24 in the weather forecast.
Yes, so
and perhaps you could answer why we use ensemble simulations, which is a series of simulations of the same forecast.
So both in weather forecasts and in climate simulation, you have to initialize your model. That means you have to prescribe temperatures, pressures, humidity, wind, all over your globe to start with. Now, if you're on a weather forecasting model, of course, you probably use your daily analysis, and you can then go forward from that. That means your measurements. With a climate model, you've got to start from somewhere. In either case, if you start from a slightly different starting point, even just a few little bits, particularly for weather forecasts, if you change the values in the tropics a little bit, you find that the whole simulation is different from what it would be with a different initialization. So weather forecasting, you need to have, and they do have these ensembles of lots of weather forecast models runs, and then they put them all into ensemble and look at the spread of the predictions, and that gives an idea of uncertainty. With climate models, we can do the same thing. Now, if you start off with lots of different, it depends on who's doing what. In answer to the question, it can be very few. It can be as few as 5, or it can be as many as 20 odd, depending on who's doing it and how long for, and what the resolution of the model is. But if you look at the bigger picture, just if you looked at the, say, global mean temperature forecast by the climate models, they have a different trajectory. You know, you see these spaghetti plots, and it's going up and down and wiggling all over the place. But the overall trajectory that is followed by the models is very much following our understanding of the basic physics. So the ensemble is giving you the spread, but the forecast, the ensemble mean forecast, is something that we sort of understand.
Okay. We have about 2 minutes left, and no more questions in the chat box. So perhaps I'll ask just one last question, and it's a question about your own research. What is the effect of changes in the sun's output?
Can I have another
hour,
please?
You know, we used to hear a few years ago that all of climate change.
Absolutely, and we've mentioned deniers, and it's quite interesting that the deniers want it to be due to the sun because they don't want it to be to greenhouse gases. And when I started working on this, I don't know, way back when, these denier people sort of somehow thought that I must be trying to prove that, and I got on various sort of email circulation lists of people who wanted to. Anyway, the answer is it's very small. It's sort of detectable. In terms of about 1/10 of a degree or so. Sorry about my clock.
I think that's giving us a hint.
on centennial timescales. On the 11-year cycle scale, so the sunspot cycle, you can see changes in weather patterns in response to the sun, which is quite intriguing, especially in the North Atlantic Oscillation and this sort of thing. But you can't see changes really in global surface temperature more than about 1/10 of a degree.
Okay, thank you very much, Joe. It's been a fascinating talk. Thank you, everybody who's participated and asked questions. Sam, I think we have some final slides to put up, but I think it's been a fantastic talk, Joe. It's I've been in this game for probably as long as you have, and I learned some things tonight. So thank you very much. Everybody, please do keep in touch with the Royal Meteorological Society. The talk will be published on YouTube and on the Royal METSOC website, and you can see the links there. You can email, you can see us on Twitter at RMetS, and you can email us at info@rmets.org. And just to remind you again about the talks coming up on Thursday, the 24th of November, a virtual webinar on our journal Meteorological Applications and a Meet the Author session. On Wednesday, the 25th of November, a virtual meeting on forecasting for dinghy regattas and giving useful forecasts at the subgrid scale. And Wednesday, the 2nd of December, on Nature's Calendar, recording the phenology in the UK. So thank you, Joe, again. Thank you, everybody, for joining. And I officially close the meeting at this point.